Alright, good afternoon everyone. So we ended last meeting here sa antenna gain. So a directional antenna can radiate more power in a given direction than a non-directional antenna. In this favored direction, it acts as if it had a gain. So when we say antenna gain class, again, it doesn't exactly mean in the same way of how we use the word gain sa amplifier. Here, I think it's better kung gamit ang illustration. So this is the radiation pattern of close enough, no? Close enough to the radiation pattern of an ideal antenna. Ideal, or we call that one an isotropic antenna. So isotropic meaning mag-radiate siya of electromagnetic energy. Number one, in all directions. And number two, the same ang power in all directions. So it's just a theoretical antenna, no, that doesn't really exist. So this one sa atong visual right now, this is the radiation pattern of a antenna close enough, no, to an ideal, to the isotropic antenna. So Marshall, yeah, pwede mo din siya ideal. So Marshall donut, no, ibang ito nga. Pero try to imagine that our antenna is exactly in the middle of this thing, exactly in the middle of this thing, and it's very small. Okay, very small, and point lang siya kibali, point, and somewhere exactly in the middle. Okay, so mala siya sort of na tuod, no, mala siya nag-radiate good of energy in all direction and same power. Now, this is an example now of a more directional antenna. This one. Okay, mas tsadaan, di ba? Okay naman on eh. Or this one. No? This one. I think, yeah, nadidire ang ang color is nag-symbolize sa strength, no? Power level sa irradiate na power, no? So red is very much very strong, whereas blue is medyo weak na, negative 10 dB na ganit dire. So nato atong visual earlier, this one, so it radiates very strong energy in all direction. I try to imagine that one, instead of ang power is naka-concentrate, instead of ang power is na in all direction, i-concentrate niya in just one direction, no? So na-compromise, may tabo, no? So na-compromise. Instead na all direction, i-direct lang niya in one kuan, no? Power beam, superheroes, no? Sa isa lang ka direction, no? So dire lang. So in any direction aside from siguro mga, I don't know, 30 degrees siguro, no? Any direction aside ani, wala yung ma-detect na electromagnetic energy, just like this one. Any direction walay color, no? Wala electromagnetic energy, so wala ma-detect. Masing usang antenna ito ato ibutang diya, dili na ma-detect ang signal, no? So instead of all direction, directed towards only in this direction, no? Ani man siya, or this one, no? This one is just exactly like ingane, no? So the antenna nato is here in the middle, no? In the middle of the azimuth and the elevation plane. Or I think elevation plane is really nakita kay kuan siya horizontal. So ato antenna is not dire. Earlier, one big circle siya, but now directed towards in this direction only ang radiation pattern sa itong antenna. So in that sense, nagkaroon, no? Kalog yun. Nagkaroon of gain ang antenna in this direction only. So that's what we mean when we say antenna gain. And still, because it is a gain, quote unquote, it's measured in dB. It's measured in, actually it's measured in dBi. Okay, so try to remember that unit, dBi. We issue the same sa before, like when we say dBm, that decibel with reference to milliwatt, no? Yeah, ang dBi is, ang iyang reference is I signifies isotropic antenna. So when we encounter that term later, or encounter antenna gain, and iyang unit of measure is dBi, nasa'y gain, it has a gain of that value compared to an isotropic antenna. So maybe the isotropic antenna has a gain of 1, no? or 0 dB. I forgot. Pero as compared to the isotropic antenna, ang gain sa atong realistic antenna is a numerical value, and yung unit of measure is dBi. So I'm sure may encounter na to na more later. So antenna gain of this type is expressed as a ratio of effective radiated power to the input power. So input over output gihapon. Okay, the measurement of power at a specific point. No? The power measured at that specific point is the output power. The input power is the power radiated by the antenna, somewhere in the middle of that radiation pattern. So this is the formula, actually. The power radiated antenna with directivity and therefore gain is called the effective radiated power. Another popular variation of a half-wave dipole is the folded dipole. All right. So, yeah, magtanong siguro, I think karon nga half-wave dipole kay folded man siguro. A folded dipole is also 1/2 wavelength long. The whole thing is 1/2 wavelength long. We know nga 1/2 siya, span sa whole antenna, and 1/4 na siya per segment. Consists of 2 parallel conductors connected at ends with one side open the center for connection to the transmission line. The impedance of this antenna is 100 ohms. So fixed siya, 100 ohms. So we need also to find a transmission line ng ako yung ani to achieve maximum power transfer. So another antenna, di ba, we mentioned early or previous meeting na ang half-wave antenna is called by many names, no? Half-wave dipole, bipole, doublet, Hertz antenna. Okay. So another antenna category is the Marconi antenna. No? So I think familiar sa ato ang mga apelyido. No? Those are the last names of the forerunners of our field, no? The field of telecommunications. So we have the Marconi antenna or the quarter wave antenna. Hanggang po siya pangalan. Marconi, ground plane vertical, or quarter wave antenna, no? Quarter wave vertical antenna. And almost all of the time, when we say Marconi, vertical na siya ng klaseng antenna. No? Nakama actually kung ang in actual, no? Siguro in practice, kung naka-structure na siya, tukod na siya, no? With respect sa ground. So from the ground up sa yung tip sa antenna, it's 1/4 wavelength long. So the same gyapon actually sa Hertz antenna, haman mapadlong ang other 1/4 ilubong sa ground. So effectively 1/2 good gyapon, no? 1/2 na siya. Pero ang nakatibaw lang is only 1/4 the wavelength. So that's why ground plane, because isa sa iyang segment is used as ground. It is similar in operation to a vertically mounted dipole antenna. You see, The Marconi antenna offers major advantages because it is half the length of a dipole antenna. Okay. So vertical polarization and omnidirectional characteristics can be achieved using a 1/4 wavelength vertical radiator. Okay. So vertical polarization, I think we mentioned that last time. So kung one direction lang or one orientation, kung vertical, so vertical polarization, horizontal polarization with respect sa Earth. So kung dual orientation, yeah, I think one is siya ang sa omnidirectional, it could radiate in both orientations. So Marconi antenna is usually fed with a coaxial cable, much like man siguro sa Hertz antenna. The center conductor is connected to the vertical radiator and the shield is connected to the ground, the Earth ground. The Earth then acts as a type of electrical mirror, providing the other 1/4 wavelength, making it equivalent to a vertical dipole. You see? So pareho lagi sila. So yahang ground acts as the other 1/4 wavelength. So naiduha ka specific examples here. It could be implemented like the one on the left and like the other one on the right. So kaning mga radials, mga conductors gyapon na sila, kung gyapon na nang perpendicular na gyapon actually sa segment sa antenna nga naka mount vertically. So, yung radial is para siya sa ground. When a good electrical connection to the Earth has been made, the Earth becomes what is known as the ground plane. The ground plane cannot be made to Earth. An artificial ground can be constructed of several 1/4 wavelength wires laid horizontally on the ground or buried in the Earth. Usually, very tabo po in practice, buried in the Earth. So if na 1/4 wavelength sa antenna ang gatibaw, the other exact 1/4 measurement is nakabury underground. I think mas better siya. These horizontal wires at the base of the antenna are called radials, and the collection of radials is called a counterpoise. Counterpoise. Okay, counterpoise day. French or something. Counterpoise. Many applications, portable or mobile radio equipment. AM communications usually utilize Marconi antenna. So katong mga na-mention ako earlier, previous meeting, I mean, ng mga antenna sa AM radio stations. Ilang radio booth nasa city, pero ilang antenna is nasa rural areas. Okay, yung mga dagko man, pag-asa, I mean, many meters long pa man usually ang length sa ilahang antenna compared sa FM radio station. So the 1/4 of it is nasa above ground, the other one is buried in the ground. So the practical effect of this design is a decrease in inductance. Kung what problem? To overcome this problem, shorter antennas are used in lump electrical components such as resistors, conductors, and capacitors maybe are added to compensate for shortening. Practical effect of this design is decreased inductance. The antenna no longer resonates at a desired frequency, but at a higher frequency. So to compensate, got a loading coil. So common na siya na pag-mitigate ano yung problem loading coil. here, no? I-add siya somewhere between that 1/4 segment of the antenna. Directivity. Okay, the first student test ability to send or receive signal over a narrow, horizontal, or directional range. So, mo man ito kung muna siya ang partner na concept sa gain, directivity. The physical orientation of the antenna gives it a highly directional response or a directivity curve, directed only at a specific direction. So it doesn't mean, example anti-antenna. Baron super antenna, no? Let's say, although atong baron antenna sa balay kay just for receiving naman na sila. Pero if we have a radio equipment na maka-transmit at that specific frequency, pwede magamit na ang atong baron antenna for transmitting, di ba? We learned before na ang atong antenna is reciprocal, no? Reciprocal meaning if maka-transmit siya at a particular frequency, technically pwede po siya if maka-receive siya at a particular frequency, pwede po siya maka-transmit at that frequency. So for example, the balloon antenna, no? Isa sa mga best examples of very directive antenna. So example, naka-atubang siya north sa inyong balay. So, then gimon nato siya as transmitter. Let's say, for example, 10 meters away to the north of the antenna or receive tagong signal. Dili siya mo follow na 10 meters sa south sa antenna is maka-receive siya the same energy or the same power level. So that's what we mean when we say directive. Directive lang siya or naka-focus lang yun ang power sa isa pa specific direction. A highly directional antenna acts as a type of filter, no, to provide selectivity, provides greater efficiency of power transmission. Directional antennas. Directivity, because it focuses power, causes, again, causes the antenna to exhibit gain, which is one form of amplification. So, ano siya? Itong 2D man siya. Kung dili man gali exactly the same, pwede siya magamit as analogy and oo, kanang directive na microphone. Ang kuan lang nun siya, kalahian lang dili man good antenna gid ang microphone. So, pero yeah, I think kanang term is ang pag-use ng term sa directive ng mic is the same sa kaning sense, no? Directive food ng antenna. Same siya concept, yeah, sakto. So, specific lang direction. Kaniyo, mas better pa ito nakita ganihan nga radiation pattern kay mas sophisticated kaysa kani. I think kaning naka-emphasize dire is exactly the same aning nasa right portion sa slide. Diba? Pareha sila. So, mas better ni. So, directed siya at that direction. No? So, napagpan sa slide. So, na siya major lobe or main lobe and ay mga minor lobes. May siya missile, no? Or key lobe sa alert. So, directivity. To create an antenna with directivity and gain, 2 or more antenna elements are combined to form an array. Okay. Array na siya ha. Pag basa. So, 2 basic types of antenna arrays are used to achieve gain: parasitic arrays and driven arrays. Okay, diba? So, kanang baron antenna, anong baron antenna na siya tuod at kabalo mo anong muna siya ngayong pangalan? Ka-remember mo sa person kung asa siya giname after? Kanang baron super antenna. Kinsa si baron? Kailan mo? Or basig wala mo kailag baron antenna, basig kaya mo sige kiskot-kiskot to. Wala mo ka relate. Balon guys. Basi wala gid mo kakuan ba? Balon antenna. Kani diba? Wala mo siguro kailan no kung kay kinsa ni pangalan after balon antenna. Kani Marconi Antenna, balon super antenna. Kani siya ang person nga sure wala gyud. Sige. Gamay lang at trivia. So pero kadto mo nang balon nga antenna or balon super antenna nga maka-pick up og signal sa ABS before. Ernie, sakto. Ernie Balon. Kung siya sa Ernie Balon na siya. Broadcaster naman niya, or newscaster naman niya siya sa kuan sa ABS. Was a Filipino broadcaster and inventor. Inventor good. Hindi ko sure kung sabayang invent. He spent more than, kung mo siya before, no, mga bata pa siguro, no. He was, to attest to this, he was the inventor of the so-called balon super antenna. Siya ginag-invent or giname lang after sa iya ha. Hindi kay ta sure ani class ha, pero so, ako pagkabulo mo giname lang after sa iya ha. So sige lang, hindi naman ako matter. Di man gizi ko niya gi-invent kay existing na nidaan nga technology. Kasi iya lang tweak gamay, no? So kani si Ernie Balon, sa una sa TV Patrol, usually ang second to the last nga part before mo end kay one man weather report, no? Siya man nga weather report sa una before. And after siyang weather report, gagawa na siya trivia. Nang ginabuhat ni Kuya Kim. Ginabuhat ni Kuya Kim. Siya na malagsaya na nga pattern before after sa weather report kay trivia siya o scientific na facts. The same siya ginabuhat ni Kuya Kim. So, yan na ang iyang personality before. So, I'm not sure lang yun kung siya yun exactly nag-invent ang balon super antenna or giname lang after sa ABS. So, I don't know. Pero sige lang, doesn't matter. Di siya exactly kung ano no, parang amar siya giyagay ng antenna. Wala lang yung mga kaning term kaning atong mention right now. Wala ning mga arrays. No? So ang yagay antenna, yagay ng sino pag yagi man usahay, yagi or yagay uda. Yagay uda. Ano siyang magyahang complete name? I think mga scientists noon sila. Si Yagay o si Uda. Yagay. Or simply, Yagi antenna. Ako man, mga Japanese. Yagi siguro kay Japanese man. Hidetsugu Yagi. Yagi Uda antenna. So, sila nag-invent din anong Yagi Uda antenna. Nabaday ko ng baron. Nabaday ka ng other nga mga lines. Like in ane. Kanang ana. Lagi two straight lines lang, no? So ang baron is malalagi siya dipole, no? Dipole antenna. So ang yagi, technically dipole lagi siya, antenna gyapon ang yagi antenna or yagay. Kanang mga karaan ng antenna sa balay, no? So mga atop sa balay sa una, manang yagi antenna. Extra siya. So ang other nga mga passive na conductors diya sa yagi antenna, dili na sa technically connected actually sa antenna, no? Kanang mga arrays, parasitic na arrays. So a parasitic array consists of parasitic array o driven array. So ang driven is kanina sa tunga, no? The driver or siyang the driven element. So parasitic ni silang naa sa kaniyang yellow line. So mga parasitic na sila. So isa lang yun diha ang active na element lang sa tunga kung asa connected ang coaxial cable. So if iyang direction is kung sa slide papasa ka, diba? So kung mauna iyang direction, sakto ba nga akong pagkuan sa webcam. Kung mauna iyang direction, gabutang taog parasitic elements in front of the main driven element to increase directivity. Para ma-restrict lang yun in that direction ang electromagnetic energy. Now, unsay purpose sa likod, no? Kaning naa sa dire. Okay? So ang purpose ani sa likod pod, kung magbutang ta og parasitic element sa likod sa driven element, kung in front, like this one, in front sa driven element to increase directivity. Ang sa likod, to reflect, no? Para wala gyud mag-escape ng electromagnetic energy in that direction. Para dito lang yun directed towards electromagnetic energy. So driven element is an antenna that has two or more. A driven array is an antenna that has two or more driven elements. Each element receives RF energy from the transmission line. Sort of ingana ang effect ends. So collinear antennas. Collinear antennas are usually two or more half-wave dipoles mounted end-to-end. Okay. Imot ko sa collinear antenna. Okay. So sa mga tower. Diba? So daghan siya og driven element in this case. Ang collinear antennas. So maging ani. Dili man noon mas kusog ang electromagnetic energy, dili man niya na. Mas directed towards lang, no? Example, instead nga ingani ang imong radiation pattern, ang directivity lang, mas more nga mo narrow, mas more nga mag-narrow. And actually, nanay specific nga mga kwan ha, nanay specific nga, di na siya basta-basta lang, mabutan lang tawag metal in front. Nanay specific nga mga sukod, medyo sophisticated na gamay. Na specific length ang first na parasitic, second sa third, I think di lang kay random na mga sizes, na sila mga specific na sizes and specific distances from one parasitic element to another, no? So I think na-solve na nila before sa na mga measurements. Pero yes, mas ma-increase ang directivity kung magbutang tag more parasitic elements. Mga idea behind. Siguro sa una, kaya nila gina sila until na perfect nila ang measurements. So collinear antennas, same ani, the same ani nga paan ng klaseng antenna. Or usually two or more half-wave dipoles mounted end-to-end, two or more mounted end-to-end. So this is one half-wave dipole, this is another half-wave dipole, another one. Collinear antennas typically use half-wave sections separated by a shorted quarter-wave matching stub, which ensures that the signals radiated by each half-wave sections are in phase. Currently used only on VHF and UHF bands because their length becomes prohibited at lower frequencies. Restrict yun sila sa frequency. Okay? The lower the frequency is, the larger the size of the antenna. Hindi man tayo pwede mga-create o so large antennas sa aning orientation, no? Mag-overlap na bali sila. So, mag-restrict sila sa mga very high frequency and ultra high frequency ng mga signal, ng mga signals. So, yung radiation pattern pinakumbasa sa of 4-element collinear antenna. So, isa sa ito makita din nga yung purpose para mas mo widen pa, no, ang radiation pattern. Pwede kayo tulo lang, no? There's this specific antenna na tulo lang ka-driven element ang kinanglan para maka-model siya o omnidirectional na antenna na radiation pattern. No? Kaya ang isa niya ka-kuan, beam width is 60 degrees man. Dili kanina nasa slide. So we have a specific antenna na yung beam width is 60 degrees. So we only need two others to complete 120 days, 120. Kanang mga antenna sa tower, I think yan na sila. So an example. So an example of nahatag. Yan ang radiation pattern sa yan eh. Sa katong collinear antenna. So the purpose of doing it like this para ma-increase ang size sa radiation pattern. No? So nag-back-to-back na sila. I think dili silo kaniyo of course important yang na asaga phase like kaning second nga siguro second picture mo siguro ni ang radiation pattern atong kato nasa slide dili siguro ning kaning first ni second kaning nasa right kani bitaw kani siya so sort of nag back to back man sila. Broadside antenna is a stacked collinear antenna. So kung itsura aning broadside antenna. So mas more complex pa, no? Mas upper layer pa compared sa collinear antenna. So if ang collinear is made of dipoles, ang broadside is made of collinear antennas. This antenna produces a highly directional radiation pattern that is broadside or perpendicular to the plane of the array. The broadside antenna is bidirectional in radiation, but the radiation pattern is very narrow beam width. So this is I think no? Bidirectional but very narrow beam width. So ang gina-solve niya na problem is ang distance, no? Mas layo pa gid niya maabtan ang distance broadside antenna. Mo siguro yung mga yung mga transmitting antennas sa kung unsa ang receiving kay atong para sa TV, no? Sa ABS, no? ABS-CBN broadside antenna. Okay. Need man nga mas taas ang maabot, no, ang distance. And fire antennas use two half-wave dipoles spaced 1/2 wavelengths apart. And one antenna din nga and fire antenna. The actual. Okay, military siguro niyo. So, ari nagyapon. And for antennas, bidirectional radiation pattern with narrow beam width, pareho naman, no? It's in the variation is the plane of the given element. A highly unidirectional antenna can be created by careful selection of optimal number of elements. So, almost the same ang concept na, no? Yeah, kani, pareho siya. Log periodic, the same gapon. Ang log periodic, yung mga magyapon ng itsura, yagay. Or yagi. Mas daghan lang siya og parasitic elements. Just like this one. So TV magyapon ay kabantay mo ani yung klaseng antenna. So na ba ni iyang main usage ba? Okay, so this is a log periodic antenna. So una mo ni ginapa-design nila sa project sa Com10. Paano dun mga aluminum na good nga mga poles. Mo connect lang kag coax sa imong i-choose na given element. Lisod man, no? Lisod man yan. Pwede naman kung initiate lang mo sa inyong own. Pero, yeah. Sa una, yan yung ipabot nila sa kanilang klase. Log periodic. Pwede naman But, kahit lang mo katong aluminum na poles, cut lang ninyo specific na mga lengths. Ang main kay connect lang coax. So aside na, ang isa sa lisod na part is so actually test. So una gina-test lang nila, connect lang sa TV. Siya itong machine test sa effectivity ani. Periodic antenna. Impedance matching, I think we've covered this before. The concept sa impedance matching sa antenna is the same magyapon sa transmission line. So pwede na ito dilig kayo mag-go deeper ani. Radio wave propagation. I think as far as these slides are concerned, muna ta sa antenna nga section, sa introduction to antennas. That one is electromagnetic wave propagation or radio wave propagation. So once a radio signal has been radiated by antenna, it travels or propagates through space and ultimately reaches the receiving antenna. Energy level of the signal decreases rapidly with distance. So take note of the second statement. Energy level of the signal decreases rapidly with distance from the transmitting antenna. Napadili ang formula na to. Define it's called the inverse square law. Electromagnetic waves. Radio waves. So when it comes to RF, distance plays clicks with the mind. The intensity of radio waves over distance obeys the inverse square law, which states that intensity is inversely proportional to the square of the distance from the source. So, sa formula ni Ani. Basta kay 1, P. P over 4 pi r squared. Okay, so P. In standard measurements, meters, watts. So what if we have a 1 watt radiate sa isa ka source, no, or point source? how much is the power 1 meter away? 1 meter is ma-convert na to na siya. Ma-comprehend na to sa nakalayo 1 meter. So, isa na calculator daw. Let P be equal to 1 watt, then 4 pi R be equal to 1 also, 1 meter. So, 1 over 4 pi 1 squared. Calculator daw. Or 1 over 4 pi. The answer. Yun yung calculator. Zero 0.796 or 1, 2, 1, 2, 3 or mga 80 milliwatts. So yan yung may tabo. If we have a 1 watt of 1 watt of energy or power transmitted at a specific point in space, 1 meter away, atong ma-measure nga power is only this one, 80 milliwatts. No? So 1 meter lang na siya. No? That's just 1 meter away. Kung 1 watt, of course, dagko magigaya ang transmitting power spod for let's say for example for FM broadcasting stations or TV stations, dagko man na ilahang transmitting power, no? Many thousand times more than 1 watt man. So ang point here is, imagine if you have 1 watt that's propagated at a point in space, only 1 meter away, only 1 meter away, paano na to na siya? 1 arm length siguro ng 1 meter, I guess, or 1 foot. So 1 meter. Ayan, siguro na. So it's only 80 milliwatts na lang. So this is one of the explanations why this is also one of the explanations why wireless power propagation is practically impossible. So marami tawag kanatong gina-joke na wireless extension wire, hindi gina siya practically mabuhat because of the inverse square law. 1 meter away pa lang, gabi na ang pag-diminish sa signals power level. That's why kanang mga wireless chargers, kinahanglan gyapon siya duol, no? Although wireless lang siya in a sense nga there's no wire connected between the cell phone and tawag niya pad. No, di ba? Kung gyapon, dual gyapon. Okay, para ma-minimize yun ang distance between the two ports. So input port, transmitting port and the receiving port. Kay power diminishes good as distance increases. So good ning second statement and a slide. The energy level of signal decreases rapidly with distance from the transmitting antenna because of the inverse square law. So asa lugar na add to sir itong 920 na milliwatts. Kay 80 milliwatts na lang man ang nabilin. No? Actually, wala man nawala ang power. No? It's just that ang 1 watt is na spread. No? Na-spread na siya at a 1 meter na radius. So at any point sa circumference or area, nasa surface area, no? at any point sa surface area, 1 point away from that transmitting first stage. So at 1 meter away atong transmitting na antenna, no, nag-transmit og 1 watt nga power na spread equally in all directions ang 1 watt. That's why 80 watts na lang ang atong ma-measure at this point. Another 1 meter away at a different location, pero 1 meter lang gihapon, you could still read 80 watts. No? Masking 1 meter upward. No? It was itong ma-measure. So katong 1 watt, again, ang 1 watt is na-spread equally in all directions sa 1 meter away sa atong 1 meter away from our transmitting antenna. So wala nawala. No? Technically, wala man na lose ang power. Ideally, this is, let's just say, vacuum sa atong situation. No? So, or free space pa. No? Free space or vacuum. So, wala man technically nawala ang power. It's just that ang power is na-spread evenly in all directions. Such that in any direction, 1 meter away from our transmitting power, you could measure 80 watts. So that's for ideal situations. So for practical situations or real-life situations, like magnetic wave is affected by objects that it encounters along the way, such as trees, buildings, large structures, large metallic structures. Notice nga, kung namo susunod sa elevator sa isang building, wala kayo signal, especially if the elevator car is made of metal. So, matter good. Weather, yeah, most especially weather, and believe it or not, daytime, no, or nighttime, time of the day. The path of electromagnetic signal takes or receive antenna depends upon many factors. No? Ano lagi dayo? Atmospheric conditions, time of the day. No? May specific time of the day kung kano sa radio wave propagation is optimum, no? So dili ideal. Dili the same ang radio wave propagation at 9 a.m. compared to 9 p.m. So radio wave acts much like light waves. So we've studied light waves last quarter when we dealt with fiber optics. So reflection, pareho lang physics sa light waves inside the fiber optics and electromagnetic waves traveling in free space. Ang bago lang siguro diri is kaning nga term diffraction. Walang nato nila encounter sa lights. Reflection, of course we know this one. Reflection also, the bending of light due to change from one medium to another. Snell's law, you encounter this one. Okay. Deflection. Deflection is something else. Deflection is the bending of waves around an object. Diffraction is explained by Eigens Principle. Assuming that all electromagnetic waves radiate as spherical waveforms from a source, each point on a wavefront can be considered as the point source for the additional spherical waves. When the waves encounter an obstacle, they pass around it, above it, or on the other side. So, yeah, nagtamalay din, no? So, again, masyaging ani class. Have you heard of this experiment? The double slit experiment? Isa yung sa mga experiment ka mo pa? Sige, explain daw, Mao. Sige, i-refresh daw ko. Sige daw, Mao.
Double slit but many dots.
Mora, isa pa man. So may implication ana.
Based anang naiisa kaning mag-refer ta ng image, sir, na mga waves. So kanang
Yes,
yes, sir. So like na light source na yun. Basta super gamay ang kuan, duha ka slits dayon. Pag pass through sa light ana, you'd expect nga duha ra ka lines ang mapakita sa screen. Pero sa base silang experiment kay daghan nga lines, then ilang na discover nga light travels in waves dayon. Ang pag-intersect, based kung aha ga-intersect o dili ga-intersect ang kuan, duha ka waves, silang mga troughs and silang crests, mao ang ga-dictate sa kuan, sa dots lines nga show sa screen.
Ay, very good, no? Nice searching explanation. Thank you, Mao. Yeah, exactly katong ingon ni Maui earlier. That's what the double slit experiment is. Patingala ta nga if duha lang ka lights, if natay light source and duha ka bangag, di ba to expectation is dapat duha lang pud ang gawas sa kuan, no? Duha lang pud ka sa ka dot nga light. Or yan nila lang. Let's just say we have ang atong slit is yan ni kadako, no? Kani bitawng bangag diri sa metal sheet, no? Let's just say yan ni kadako, no? Plus kadako sa akong ulo, ang sigo akong ulo yan. Notice mag-flash na dito og laser pointer, no? So what would you expect sa screen after sa metal sheet, dire? So you'd also expect duha ka dot sa laser, no? Of course, understandable. But what if flashlight, no? Flashlight ang ako i-flash sa kanina ko. So mani mo gawas, no? Many slits. Anong daghan nga slits ang gawas is because katong we mentioned ni Maui earlier, ng mga troughs and crests. Mo dito ang technical term ani, no, I forgot na sa una. Basta kay light, ganun no? Mas better to ng mga terms actually. So it's because light travels not only as particles, as what physicists have learned before, but as waves also the eye, light waves like siya. So in more simpler terms siguro, ang yung implication ani is in corners, no, or at corners, sa mga corners, kung may tabo class is weird kayo, no? When electromagnetic waves hit very sharp corners, what would happen is mag-create siya og another electromagnetic na source. No? So mala siya as if new na point source. I think kanitanan nga mga visual diri mao man ang gina point out, no? Like this one, no? So only ang reason class nganong naagya po yung signal sa Wi-Fi signal sa atong kwarto bisan pag ang router is nasa gawas, no, sa kwarto or nasa other room. It might be perhaps because nilahos ang electromagnetic wave sa door, no, sa material mismo, or it's also because sa sharp corners atong door, sa walls, pagbangga sa electromagnetic wave dito, and create na po siya another electromagnetic na source, no? So muna ang effect sa mga corners to the electromagnetic wave, and muna siya ang explanation sa Eigens Principle. Assuming that all electromagnetic waves radiate as a spherical waveform from a source, each point on a waveform can be considered as a point source for additional spherical waves. When the waves encounter an obstacle, they pass around it, above it, and on the other side. No? So pass through lagi po sila. No? As the wave front passes the object, the point source of waves at the edge of the obstacle creates additional spherical waves that penetrate and fill in the shadow. Sa slide. the shadow zone. Fill in the shadow zone. So if wala kayo tayo na nabalaan ng physics, no? That's how we try to look at it. In corners, may mo siyang another point source if na electromagnetic wave mo bangga sa corner. So pag yan may tabo. That's Eigens Principle, and that's diffraction. That's diffraction. The bending of light waves around the corner. So marami na siyang simple nga pag-explain sa diffraction, pag bending sa light waves around the corner. So the actual diana, when the light wave hit a corner, it spreads out again. So dala, so transmitter here, we have a building. The building, of course, we know has a sharp corner here sa northeast and isa sa southeast. So when electromagnetic waves hit these corners, they become new point sources. So point sources along wave fronts will lose new spherical fronts. Like one ani sa YouTube, mas better, no? Video. Ito yung actual ng papel-papel na. Wala ko madung mga Wi-Fi, about Wi-Fi to siya nga video. Lang, tugayan ko kung pangitaon. Basta kay, nato isa ka video nga nakita nga, tsada ang pagka-visualize sa Eigens Principle. Particularly sa Wi-Fi signal. Ako lang ito pangitaon siguro later. So radio wave propagation through space. When we say space, actually it's not outer space, but well, space, no, a place somewhere. So we have three types of radio wave propagation, like ground wave, sky wave, and space wave. Usay mag-matter kung kinsa ang source ani. Na usay ilang refer sa ground wave at sa ground wave space wave di. So when we say so surface wave, ang surface wave of ground wave is iyang giusa, which is logical, no? So when we say ground wave or surface wave, the transmitter uses the surface of the earth to propagate electromagnetic signal. So kung kuan pa, bisayon pa nato ni, musubay ang electromagnetic wave sa surface sa earth. So magiging ani. If we have an antenna designed exactly for this purpose, and ang frequency po sa atong signal is optimum also for surface wave propagation, what will happen is the electromagnetic wave will travel along the surface of the earth, no? Ideally. Yeah. So that's for ground waves. Ang sky wave is, ang antenna is bend upward, no? Para mo travel siya. Sa sky. No? So there's this portion of the atmosphere, guys, that we call the ionosphere. So it's called ionosphere because of the presence of charged ions. And these ions are present because of the sun, no? Because of the rays of the sun. So the ionosphere disappears during nighttime. I think so far sa akong pagkadomdom, no? Is there ionosphere at night? When night falls, the ionosphere thins out as previously ionized particles relax and recombine back in with the particles. Yeah. We could say during nighttime, ideally the ionosphere disappears. Wala naman ang sun. Wala naman mag-charge sa mga particles sa dito nga portion sa atmosphere. Okay? So what would happen is during daylight, no? During daylight lang sa ning situation, kung time na ang ionosphere. If our antenna is transmitting electromagnetic wave energy through skywave, no? Nice specific angle and specific na frequency ang signal nga magically if ipa-travel ni antenna upward ang signal, mo bounce siya, no? Mo reflect. Just like this one. Nag-reflect ang atong electromagnetic energy. So nahimo nga mirror atong ionosphere for electromagnetic wave. No? And again, that's for specific frequencies only. So na a range of frequencies where skywave propagation is possible. No? Not all. And it's also possible na for those kinds of specific frequencies, optimum for skywave propagation, dapat at the right angle po. Okay, kung sobrang po kataas, it's possible na mula ho sa side ng atong electromagnetic energy. Just like this sa slide. So, many telecommunication companies take advantage of skywave or take advantage of the ionosphere in daytime, no? To transmit longer distances. Dili makaya for ground wave and space wave propagation. Supposed to be una tatong space wave. No? Pero skywave na dili una. So if dili makaya ang space wave propagation or ground wave, no? Again, ground wave is gamiton ang surface sa Earth. No? Example na yung table. No? I think you have tables in front of you, man. No? Try to put your arm or hand, I mean, on one side of the table, and your hand on the other side of the table. No? So mag-transmit silang duha. Okay? So then ang table din ang surface sa Earth. No? Pero so you know, ang Earth dili man horizontal, no? Siguro in a journal, siguro flat earthers dili. So we know na ba na ang Earth is may curve, no? May J curvature ang Earth. So infinite ground wave propagation is also not possible, no? Infinite surface wave propagation. Kay as electromagnetic waves travel along the surface of the Earth, ang vertically polarized electromagnetic signal kay magsige na siya bend. Magsige na siya bend as it travels along the surface of the Earth until the time nga ang angle between the electromagnetic wave and the surface of the Earth is 0 degrees or parallel na sila. No? So kung mo-travel ang electromagnetic wave sa curvature sa Earth, along the surface of the Earth, magsige na siya bow until mawala. No? So dili infinite ang pag-travel sa electromagnetic wave sa Earth na mutuyok siya. No? Nai point kung ano sa papalong na dayon. So dapat before that time, nai antenna. So kung dili na siya possible, pwede ta mag-line of sight communication. So another term for space wave communication is naman dito sa slide, line of sight communication. So ang line of sight communication, that is what we call that's another technical term for space wave propagation. So na ay direct nga wireless connection between the two antennas. So that's for ground wave, space wave, line of sight. So kung dili pa gid makaya, that's when we will use skywave propagation. Skywave. mas taas man ang ma-cover nga distance kung ipa-reflect ni transmitter ang electromagnetic wave sa clouds and sa atmosphere, then o bounce siya padulong sa transmitter many miles away. So that's skywave propagation, and this is only possible during daytime, when the sun is up, and this is optimum, or the ionosphere is rich with charged particles. Kasi makaguess at what time of the day man? During kung sa time of the day ka optimum ang skywave propagation if it takes advantage of charged particles in the ionosphere. Yes, noon, no? At noon. At noon during a bright and sunny day. No? So dili para sa aning weather nga nato karon, no? So dili na siya optimum for skywave propagation because wala may sun, no? So, pwede gyapon, no? Pwede man gyapon kay maybe na other parts sa maybe ang transmitting part is sunny dito, no? Sa receiving ng siguro dili. So dili gyapon optimum. So optimum siya at 12 noon in a bright and sunny and clear skies. So you could look up the ionosphere sa Google, pwede mo natanawon for a more detailed visual on what the ionosphere is. So radio wave, space wave propagation, I will cite, very easy to understand. So for space wave, direct na line of sight propagation, we have this formula to solve for the distance between the two transmitting antennas, considering wala obstacle, the peak of the curvature of the Earth. So this formula is D is equal to square root of 2HT plus 2HR. HT and HR are the height of the antennas. So dapat ang height is high enough na ma-overcome niya ang peak curvature sa Earth. So, tama na din ang mga formula, no? Very common ni siya nga formula. Usay, mugawas ni siya sa mga quiz bee sa JSEP. Usay, mugawas ni sa board exam. So, take note lang ani. Kaya lang mo din Horizon. Of all the formulas sa comms, especially sa com 10, nga dalit man dumduman, it's this one. That's why usually mugawas gid ni siya ng mga questions. So if dili kaya, no? Dili ni kaya, let's say napag-mountain dire, somewhere in between, it's advisable to use repeaters. The repeater stations extend the communication distance at VHF and HF and microwave frequencies. So I think we know how repeaters work, man. And this is also the concept behind satellite communications. Transmitting and receiving antenna might be on the Earth, and instead of it's tilted upward, and ang atong satellite is somewhere here, to suspend. I think if dagan patag time makaabot ta og satellite comms before we end this semester. Okay, I think wala na ilain nga subject na makatopic of satcom aside from content. Wala man ta siya sa syllabus, pero pwede na nato apilon. Okay, important po siya. Fading. Fading is a variation of signal amplitude at the receiver caused by characteristics of the signal path and changes in the signal path. So, especially within the context of link budget calculations, isa sa biggest factor na itong ina-consider is of course a distance, no? The inverse square law, as explained earlier, restrict us from lengthening, no, the distance between two antennas, the transmitter and the receiver. Okay, So even in ideal conditions, even if vacuum ang space between the two antennas, signal level will still drop. No? How much more in a more practical na situation, no? More realistic real world situations. So, hindi rin musulod si fading. Okay? Lahi tong kaganina at lahi tong attenuation due to distance, no? I think it's just a matter of the terms na i-use. So, maybe atong refer to dropping of the signal level due to distance, which is natural, no? Which is really natural. Maybe pwede na ito gamitin term na attenuation ato. Signal attenuates, the attenuation of signal increases with distance, no? And that's normal. Fading is another kind of phenomena. Hindi na din musulod ang mga losses due to the environment. No? So, kato mga na-mentioned earlier, like weather, obstacles, squeeze, lahi nga fading number ang atong i-subtract sa atong link budget. Kung ato take into consideration ang lahi po ng mga environments, no? Kung forest ba, lahi po na siya nga number. Kung desert, lahi po, no? So lahi nga situation, lahi po nga dB loss atong i-introduce sa atong budget na formula. Weather, lahi po, no? So, daghan. And we collectively term those mga environmental nga mga factors as fading. No? Ang pag-degrade sa signal due to external na mga factors, no? Fading. So, diversity. I think lahat na po din siya nga no? Hindi siya necessarily connected sa fading. Diversity is the situation when we utilize two or more of something, no? So we have frequency diversity and spatial diversity. So frequency diversity, balikan na to tong atong na-learn sa COM9, COM8 ba to? Katong multiplexing of frequency division multiplexing. Diba? If you remember, FDM is the transmission of digital signal using two different frequencies. So pwede na siya mo tandem aning frequency diversity uses two separate sets of transmitters and receivers operating on different frequencies. No? So again, when you say diversity, it's the usage of two or more of something. In frequency diversity, the use of two or more transmitters or two separate sets of transmitters and receivers operating at different frequencies. Dahil po lang spatial diversities. When you say spatial diversity or space diversity, two separate receivers and in this case is two receiving antennas spaced far apart. No? So ang many here is the receiving antenna. No? So isa pa kabuk-an ang transmitting. No? Duha ang receiving antenna. So spatial diversity. Basta kay when we say diversity, again, it's the usage of two or more of something, no? To overcome multiple problems, no? Or challenges. That's the idea. So we'll cover more of fading and link budget calculation again, no, for antenna systems. A little more as we progress next week, 2 weeks from now. So we'll end our introduction to antenna and radio wave propagation here.